SwayamPrabha. Digital India. Educated India.
In this lecture, I am going to continue further with symmetries and conservation laws. This is the overview of what we are going to discuss in this lecture. We are going to introduce this concept of cyclic coordinates. In a moment, we are going to see what they are. We are going to discuss infinitesimal symmetry and the corresponding conservation, which goes by the name Noether's theorem. This Noether, M. E. Noether was a famous mathematician in Germany, and who came up with this idea of symmetry and conservation. First, we are going to look at cyclic coordinates. What are cyclic coordinates? Cyclic coordinates are those coordinates, those generalized coordinates, which appear only as generalized velocity, not as the coordinate by themselves in the expression of the Lagrangian. Therefore, a cyclic coordinate appears only as generalized velocity and not the coordinate itself in the Lagrangian. For example, if you have a Lagrangian which is in general function of so our system has generalized coordinates q1 and q2, but the Lagrangian looks like this. It is a function of q1 dot and q2 dot. q2 is missing. Therefore, the coordinate q2 is a cyclic coordinate. In the Lagrangian expression, q2 does not appear, but its generalized velocity of course appears, q2 dot appears, but q2 does not appear. Therefore, q2 is a cyclic coordinate. And what happens? Why this is important? Just recall the equation of motion, Lagrange's equation of motion corresponding to the coordinate q2. It is d dt of del L del q2 dot minus del L del q2 equal to 0. Now, if q2 does not appear in the Lagrangian, then del L del q2 must be 0, and if that is 0, it means a total time derivative of del L del q2 dot. And what is del L del q2 dot? We have seen in the last lecture that del L del q2 dot is the momentum conjugate corresponding to the coordinate q2, or the generalized momentum corresponding to the coordinate q2. What therefore it says, in the presence of a cyclic coordinate, the total time derivative of that generalized momentum is 0. This is generalized momentum, we will call it p2, and that is 0. The total time derivative of p2 is 0 means what? p2 is conserved. It is a constant quantity. It is conserved as the system evolves. It is a constant of motion. These are called constants of motion. Therefore, corresponding to a cyclic coordinate, the generalized momentum corresponding to the cyclic coordinate is conserved, or the momentum conjugate to of a cyclic coordinate is conserved or is constant of motion. And of course, you have to observe that I have considered this equation of motion without external forces. If there are no external forces, then only this statement is true. Therefore, no external or generalized forces, generalized momentum corresponding to the cyclic coordinate is conserved. Now, this is an interesting observation, that the generalized momentum can be a constant of motion, or it can be conserved quantity if a coordinate is cyclic, and there are no external forces of course. When you have a linear displacement coordinate as a cyclic coordinate, the conjugate momentum is the linear momentum which is conserved. If it is an angular coordinate which is cyclic coordinate, then the angular momentum is conserved, because we have seen this interpretation of the momentum conjugate to that coordinate. If it is an angular coordinate, then angular momentum is the momentum conjugate. If it is a linear displacement coordinate, then the momentum conjugate is linear momentum. Therefore, under no external forces or generalized forces, if you have a coordinate, a generalized coordinate to be cyclic, then the corresponding conjugate momentum is conserved. Let us look at some examples. A particle on a frictionless horizontal surface. Horizontal surface, I am considering the xy plane to span the horizontal surface. Our Lagrangian has the kinetic energy, no potential energy, it is all frictionless, no spring, etc., no potential energy, therefore, it is only kinetic energy. Both x and y are cyclic coordinates. There is no presence of x and y in the Lagrangian, but x dot and y dot are present only. Therefore, x, y are cyclic coordinates. Therefore, the momentum conjugate to x and momentum conjugate to y are conserved. And if you just do that calculation, what is the momentum conjugate to x? It is mx dot, which means linear momentum in the x direction. Similarly, the momentum conjugate to y coordinate is my dot, and that is linear momentum in the y direction. So, both of them are conserved, there is no other external force. A projectile, the Lagrangian is 1/2 mass of the projectile times the velocity square minus mgy, where the ground is the datum. Very easily you can see that x is a cyclic coordinate, there is no presence of x. Therefore, momentum conjugate to x, which is linear momentum, x is a linear displacement coordinate. Therefore, momentum conjugate to x, which happens to be mx dot, as you can calculate very easily, mx dot is linear momentum in the x direction, that is conserved. And that you know that momentum for a projectile, the momentum in the horizontal direction is conserved. Pendulum on a free cart. We have written the Lagrangian of this system before, I have just written it here. The datum for the potential energy is the x axis. Here you will find that there is no presence of x, whereas theta dot, theta other coordinate theta dot and theta both are present, but x is not present. X dot is present of course, but x is not present. Therefore, x is a cyclic coordinate. And what is the interpretation of this? The momentum conjugate to x, which is linear momentum in this case, is conserved. So, linear momentum of the system in the x direction is, in the x coordinate direction is conserved. Let us consider this example of two blocks on a frictionless surface connected by a spring. I have taken the coordinates, I am measuring the coordinate locations of the two point masses, we are considering them as point masses, from a certain datum x1 and x2, and that is the origin. If I do that, I write the Lagrangian, it involves x1, x1 dot, x2, x2 dot, everything is involved. So, therefore, we think that there is no cyclic coordinate in this. Therefore, immediately we cannot see whether something is conserved or not. We do not see a cyclic coordinate here. Let us look at the same system, but now my coordinatization is different, the coordinatization scheme is different. I mark the location of m1 from a certain datum from the origin as x1, and x2 is the coordinate of m2 with respect to m1. Now, I write down the Lagrangian once again, it should be straightforward for you to see how to write the Lagrangian. This is the Lagrangian, and definition of x1 and x2 has changed from the previous case that we have considered. Here you will find that x1 is x1 dot is present, x2 dot is present, x2 is present, but x1 is missing. Therefore, x1 is a cyclic coordinate. See, x1 is a cyclic coordinate, but then it is something worrisome. In the previous coordinatization scheme, I did not see any cyclic coordinate. In this scheme, I see a cyclic coordinate. Therefore, I can very easily detect something which is conserved, the momentum conjugate to, corresponding to x1. Therefore, what we learn from this example is that choice of coordinates can hide your cyclic coordinate, and because if you have if you can see a cyclic coordinate, that makes it very easy, you have a constant of motion, and we all the time use constants of motion to integrate systems. We have used linear momentum conservation, or angular momentum conservation, energy conservation. These are all constants of motion, and we are going to see how, and corresponding to they all exist corresponding to a certain cyclic coordinate. Therefore, if you are not able to see a cyclic coordinate, then you are not able to immediately see the conserved quantity. In order to see this or to bring this out, we need to study infinitesimal symmetries of the Lagrangian. We are going to now study symmetries of the Lagrangian. Now, what is symmetry of a Lagrangian? Suppose you have this Lagrangian in terms of the generalized coordinates, generalized velocities. Imagine a smooth transformation, an infinitesimal smooth transformation. What is a smooth transformation? You have a new set of coordinates z, which is a function of t and sigma, some scalar sigma, such that z t comma 0, when sigma is 0, then it coincides with the generalized coordinate that we have. Sigma is a scalar parameter. When sigma is equal to 0, then this definition of z will give me my generalized coordinates. But if there is a non-zero sigma, then it will deviate from the generalized coordinates. I will look at some examples. Suppose z is equal to a rotation matrix which is function of some angle, some rotation angle sigma into the generalized coordinates, some rotation angle into some rotation, some transformation, multiplicative transformation, such that r at 0 is the identity, r capital R at 0, sigma equal to 0 is identity, then you have such a transformation. Or you have z is equals to the generalized coordinate plus sigma times another vector, an unknown vector, arbitrary vector b, but a constant vector. Arbitrary constant vector b times sigma is added to our generalized coordinate. You put sigma equal to 0, you will get back your q, the generalized coordinates. First one we will call rotation, the second one is shift or translation, etc., and there is a definite translation direction b. Now, if I use this z in place of q, I just put that z, and remember z is a function of that sigma. If I put sigma equal to 0, I will get back my original Lagrangian, but if I do not put sigma equal to 0, I may get a new Lagrangian, and that I indicate by L tilde. Of course, L tilde with sigma equal to 0 must be equal to our original Lagrangian. But now, let us make a supposition. Suppose I have been able to find out or structure my z, the definition of z, such that the new Lagrangian L tilde is same as the original Lagrangian L as a function of q. That means, this new Lagrangian is somehow independent of that sigma, even though in the transformational equations I have that sigma, but when I substitute in the Lagrangian, somehow for some reason it does not depend on sigma. For all sigma, it becomes equal to the original Lagrangian. It can happen. I am going to show you examples. Then we say that the Lagrangian is symmetric under this transformation. We will say that the Lagrangian is symmetric under this smooth transformation, or the infinitesimal transformation will come to a little later. Under this smooth transformation, the Lagrangian is symmetric. Here the word symmetry is interchangeably used with invariance of the Lagrangian. A Lagrangian is invariant under this transformation, therefore, we call this a symmetry. And this can imply that, this is very easy to see, that d sigma of the new Lagrangian at sigma equal to 0, if that is equal to 0, which means that the new Lagrangian does not change with sigma. It does not change with sigma. d sigma is the change of the Lagrangian, new Lagrangian with respect to sigma. d L tilde d sigma is the change of the new Lagrangian with respect to sigma, or the variation of the new Lagrangian with respect to sigma. Now, this variation at sigma equal to 0 is equal to 0 means that the Lagrangian is symmetric under this transformation from q to z. This is our definition of infinitesimal transformation, symmetry under infinitesimal transformation. We are saying that if I make an infinitesimal change in my transformation around sigma equal to 0, my Lagrangian is not changing. In that case, we say that the Lagrangian is symmetric under that infinitesimal transformation. Now, what happens? Why are we discussing this? Why we are interested in these kinds of transformations under which the Lagrangian does not depend on sigma, the smooth parameter? The reason is that if you can find out a transformation, a parameter, single parameter dependent transformation under which the Lagrangian has this property, then it tells us something about a conserved quantity that exists. How do we see that? Here I have outlined the steps. What is d sigma? How do you define d sigma? This is our Lagrangian. In general, it will be a function of sigma because we have put z as a function of time and sigma. Of course, remember that sigma equal to 0 will give us q, but right now we have a general sigma and we are trying to find out d sigma. Later on we will put sigma as 0. After taking the derivative, we are going to put sigma as 0. What is d sigma of L tilde? We take partial derivative. We are using chain rule. Del L tilde del z, the first argument is a vector argument, dot z prime. Z prime means partial derivative of z with respect to sigma, and to that I add the partial, again the chain rule, partial derivative of the new Lagrangian with respect to the velocities z dots, dot z dot prime, again z dot prime means del sigma of z dot, and that is all to it, and this must be calculated at sigma equal to 0, and that is equal to 0. This is our condition. This is the symmetry, that equal to 0 is the symmetry condition. This is the symmetry condition. Now, this is our Lagrange's equation for the new transformed thing, and we have seen that the structure remains invariant. This is our Lagrange's equation for the new coordinates z, d dt of del L tilde del z dot must be equal to del tilde del z. Now, this we are going to use. Now, del L tilde del z, the first term here, that can also be written as del L, the original Lagrangian del q. This you can check very easily because the first coordinate, first argument was q, second argument was q dot, and that we have replaced by z. Therefore, del L tilde del z must be equal to del L del q, and del L tilde del z dot must be equal to del L del q dot. This is a very standard property which you should be knowing. Now, this at sigma equal to 0, this is correct, definitely true at sigma equal to 0. This is definitely true at sigma equal to 0. Therefore, I am remember that I am always considering that sigma equal to 0 condition, then these equalities do hold. I am still writing out of the bracket this sigma equal to 0, but on the back of my mind I always have that thing that ultimately I am going to put sigma equal to 0. Therefore, I replace del L del Z from here, that I replace here in place of this, and del L del Z dot is nothing but del L del Q dot, which I have written here, and d dt of that. So, this step I have done, and that dot Z prime, remember Z prime is del Z del sigma. So, that term remains here, plus del L tilde del Z is at sigma equal to 0, del L tilde del Z dot, del L tilde del Z dot is nothing but del L del Q dot, of course at sigma equal to 0, dot this Z dot prime, and I will take sigma equal to 0. Here I have already taken sigma equal to 0 in these terms, it remains only here, there I will put sigma equal to 0. So, this must be equal to 0, the whole expression must be equal to 0 because of the symmetry. Now, you know that this term is nothing but the momentum conjugate corresponding to the coordinate q. So, this is the momentum, the generalized momentum vector, del L del Q dot vector is the generalized momentum vector. Therefore, this first term becomes dp dt dot Z prime plus this is again p dot d dt of Z prime, and Z prime remember is del Z del sigma. The term in the bracket, the expression in the bracket here, I can write as total time derivative of p dot Z prime at sigma equal to 0, and that must be equal to 0. So, I have pulled this d dt out, and p of course is the generalized momentum. What this tells us is that p dot Z prime at sigma equal to 0 is a conserved quantity. Why? Because d dt of this term is 0. In other words, this term itself must be a constant of motion, it does not change with time. Therefore, if we have a symmetry of the Lagrangian, we can find out a conserved quantity like this, if we can find out such a transformation under which the Lagrangian remains symmetric. Now, p is the generalized momentum dot Z prime at sigma equal to 0. Now, what is Z prime at sigma equal to 0 is something which we have to discuss a little further. This is known as the infinitesimal symmetry infinitesimal generator of that symmetry transformation. Z prime at sigma equal to 0 is the infinitesimal generator of the symmetry transformation. Why we call this Z as symmetry transformation? Because under this coordinate transformation from Q to Z, we find that the Lagrangian does not depend on sigma, at least infinitesimally it does not depend on sigma. d d sigma of the new Lagrangian L tilde is equal to 0 at sigma equal to 0. Therefore, around our unperturbed system, if I give a transformation, a small infinitesimal transformation, then the Lagrangian is not changing. That is the meaning of d L tilde d sigma at sigma equal to 0 is equal to 0. That means, around that sigma equal to 0, which is our original Lagrangian, if I give a transformation, an infinitesimal smooth transformation, then Lagrangian is not changing. Then we say that there is a conserved quantity, and how to find that conserved quantity? You find out the generalized momentum, dot it with the infinitesimal generator of that symmetry transformation. Z prime at sigma equal to 0 is the infinitesimal generator of the symmetry transformation. Then that quantity is conserved. For example, if Z is q plus sigma b, what is the infinitesimal generator of this transformation? We have to just find out del Z del sigma at sigma equal to 0, and that is nothing but b. Del Z, so here del Z del sigma at sigma equal to 0 is nothing but b, and therefore, b is a translation direction. The generator is just a constant translation of our coordinates. Now, with this we come to the Noether's theorem. What we have shown is associated with every infinitesimal symmetry of the Lagrangian, there exists a constant of motion or a conserved quantity. This is Noether's theorem. So, we have kind of shown Noether's theorem. So, associated with every infinitesimal symmetry of the Lagrangian, there is a constant of motion. What is the plan therefore? Try to find some z which is a function of t and sigma such that z, of course, z at sigma equal to 0 is our generalized coordinate, and z is a kind of transformation on our coordinates, and I have shown you some examples of such transformations. Try to find out z, this transformation, such that with this property such that d sigma of the new Lagrangian that you obtain by using z calculated at sigma equal to 0 equal to 0. That means, it is symmetric under this transformation. Try to find out a transformation under which the Lagrangian is symmetric, or at least it is infinitesimally symmetric. Then we can say that a certain quantity, if you can find that, if you are lucky enough and you can find that, then you can immediately write down the conserved quantity. Just calculate from the Lagrangian the generalized momentum and dot it with the infinitesimal generator of that symmetry transformation. P dot z prime at sigma equal to 0 is a constant of motion. Let us look at some examples. Suppose you have a cyclic coordinate. Here I do not find q2, so q2 is a cyclic coordinate. Think about a transformation z1 z2 is equals to q1 q2 vector plus sigma 0 1. That means, I am giving a shift to only the q2 coordinate, and this is a symmetry transformation, because it will hardly matter, because q2 is anyway not there, whether I add sigma, whatever value of sigma I add, it will hardly matter. This is a trivial example, but what I am trying to show is that everything falls under the scheme of things under Noether's theorem. Here the example of that infinitesimal symmetry or the infinitesimal generator is very easy, because q2 is a cyclic coordinate. Therefore, any shift in that q2 direction in the new definition of our z is going to leave the Lagrangian symmetric. Not just infinitesimal symmetry, this is finite symmetry. It is not just d sigma of L tilde, it is a finite symmetry. Anyways, if a finite symmetry is satisfied, infinitesimal has to be satisfied. Okay. Then so this is a trivial example. Now let us see what is conserved. What is the generator of this symmetry transformation? Why do we call this as symmetry transformation? Because we know that Lagrangian is not changing under this transformation. So, it is a symmetric transformation. We first try a transformation. If the Lagrangian is invariant under that transformation, then we start calling it the symmetry transformation. It is a symmetry transformation, because the Lagrangian is invariant under it. If an infinitesimal symmetry is generated, that means d L tilde d sigma is equal to 0 at sigma equal to 0 is 0, then we say that the transformation is an infinitesimal symmetry transformation. Now, every finite symmetry transformation is an infinitesimal symmetry transformation, and infinitesimal generator of the symmetry transformation is d z d sigma at sigma equal to 0, and that happens to be 0 1. We have found out the infinitesimal generator of the transformation. Generalized momentum, what is generalized momentum? It is del L del q 1 dot and del L del q 2 dot. This vector is the generalized momentum vector. This is the generalized momentum vector. And what is the conserved quantity? The generalized momentum vector dot the generator of the infinitesimal symmetry transformation, which is d z d sigma at sigma equal to 0. And if you do that, if you do that calculation, this is our generalized momentum dot this is our generator. So, this dot this will give you del L del q dot q 2 dot del L del q 2 dot, which is nothing but the momentum in the momentum conjugate to q 2. This is the generalized momentum corresponding to the q 2 coordinate, and that is conserved, and that we know from cyclic coordinates. We know that generalized momentum is a constant of motion. Now, we come back to that example with our original scheme of coordinatization, where we do not see that symmetry, we do not see the cyclic coordinate. You see in the Lagrangian, which I have written out, x 1 dot, x 2 dot, x 1, x 2, everything is present. We do not see that any cyclic coordinate in this, but let us try to find out whether we can have a symmetry transformation. Let us try a transformation, we transform it to z 1 z 2 space, where z 1 is our original x 1 plus sigma and z 2 is our original x 2 plus sigma, and this falls under the category of our it satisfies our transformation, because if you put sigma as 0, then you will find z 1 going to x 1 and z 2 going to x 2 as we desire at sigma equal to 0. Now, if I time derivate, I will find x 1 dot as z 1 dot and x 2 dot as x 2 dot, z 2 dot as x 2 dot, and the new Lagrangian L tilde in the z space z z dot is same as the Lagrangian in the x space. Why? What has happened with this? What has happened with this x 2 z 2 minus z 1? Because the sigma is same sigma is added to both of them, that gets cancelled out, and that is why we have this symmetry. Therefore, this transformation is now a symmetry transformation, and this is also an infinitesimal symmetry transformation. This is a finite symmetry transformation as well as an infinitesimal symmetry transformation. Therefore, the Lagrangian is symmetric under this transformation. Therefore, this implies there must exist a conserved quantity, and how to find out that conserved quantity? We find out the infinitesimal generator as I have shown here, d z vector d sigma at sigma equal to 0. This is the infinitesimal generator, and that happens to be 1 1. Then this follows from this. The generalized momentum, you can find out the generalized momentum del L del q del L del x 1 dot and del L del x 2 dot, and that you will get these two terms. The generalized momenta are like this, m 1 x 1 dot, this is standard linear momentum. And what is the conserved quantity? This generalized momentum vector dot the generator, and if you do that, you will get m 1 x 1 dot plus m 2 x 2 dot. This is conserved quantity. And what is this conserved quantity? This is the total linear momentum of the system, which we know is conserved because there is no friction, there are no other forces. Linear momentum of this system is conserved. We have recovered back for a trivial example possibly, but I have demonstrated the steps, and this works for more complicated systems, more general systems. To summarize, we have looked at the concept of cyclic coordinates. We have seen the if you have a cyclic coordinate, then there are conserved quantities and how to find that the generalized momentum corresponding to that cyclic coordinate must be conserved. This concept we have seen, and finally, we have generalized this notion using the Noether's theorem, in which we try to find out certain transformations under which the Lagrangian is symmetric and possibly infinitesimally symmetric, and then we call such transformations as symmetry transformation or infinitesimal symmetry of the Lagrangian. And if you can find out for a given Lagrangian, if you can find out such an infinitesimal symmetry of the Lagrangian, then you can very easily find out the conserved quantity. Therefore, finally, our task boils down to finding out infinitesimal symmetry transformations of the Lagrangian. Now, this can be an easy or a hard task, but then it brings the task of finding symmetries or constants of motion or conserved quantities to an exercise in analysis. You can do algebraic jugglery and things like that, and come up with, if you can come up with such symmetry transformations, then you can very easily find out the conserved quantities or constants of motion. So, this is what we learned in this lecture. With that, I will close this lecture.